So we'll now think about the extreme value theorem, which we'll see is a bit of common sense. But in all of these theorems, it's always fun to think about the edge cases. Why is it laid out the way it is? And that might give us a little bit of more of intuition about it. So the extreme value theorem says if we have some function that is continuous over a closed interval, let's say the closed interval is from a to b, and when we say a closed interval, that means we include the endpoints a and b, that's why we have these brackets here instead of parentheses, then there will be an absolute maximum value for f and an absolute minimum value for f. So then that means there exists, this is a symbol for the logical symbol for there exists an absolute maximum value of f over interval and absolute minimum value of f over the interval. So let's think about that a little bit, and this probably is pretty intuitive for you. You're probably saying, well, why do they even have to write a theorem here, and why do we even have to have this continuity there? And we'll see in a second why the continuity actually matters. So this is my x-axis, that's my y-axis, and let's draw the interval. So the interval is from a to b. So let's say that this is a, and this is b right over here. Let's say that this right over here is f of a. So that is f of a. And let's say this right over here is f of b. So this value right over here is f of b. And let's say the function does something like this. Let's say the function does something like this over the interval. And I'm just drawing something somewhat arbitrary right over here. So I've drawn a continuous function. I really didn't have to pick up my pen as I drew this right over here. And so you can see, at least the way this continuous function that I've drawn, it's clear that there's an absolute maximum and absolute minimum point over this interval. The absolute minimum point, what seems like we hit it right over here when x is, let's say this is x is c, and this is f of c, right over there. And it looks like we hit our absolute maximum point over the interval right over there when x is, let's say that this is x is equal to d, and this right over here is f of d. This right over here is f of d. So another way to say this statement right over here, if f is continuous over the interval, we could say there exists a c and d that are in the interval, So there are members of this set that are in the interval such that, and I'm just using the logical notation here, such that f of c is less than or equal to f of x, which is less than or equal to f of d for all x in the interval. For all x in the interval. Just like that. So in this case, they're saying, look, we hit our minimum value when x is equal to c. That's that right over here. Our maximum value when f is equal to d. And for all the other x's in the interval, we are between those two values. Now, one thing, and we could draw other continuous functions, and once again, I'm not doing a proof of the extreme value theorem, but just to make you familiar with it and why it's stated the way it is. And just you could draw a bunch of functions here that are continuous over this closed interval. Here, our maximum point happens right when we hit b, and our minimum point happens at a. For a flat function, we could put any point as a maximum or the minimum point, and we'll see that this would actually be true. But let's dig a little bit deeper as to why f needs to be continuous and why this needs to be a closed interval. So first, let's think about, why does f need to be continuous? Well, I could easily construct a function that is not continuous over a closed interval that where it is hard to articulate a minimum or a maximum point. And I encourage you, actually pause this video and try to construct that function on your own. Try to construct a non-continuous function over a closed interval where it would be very difficult, or you can't really pick out an absolute minimum or an absolute maximum value over that interval. Well, let's see. Let me draw a graph here. So let's say that this right over here is my interval. Let's say that's A, that's B. Let's say our function did something like this. Let's say our function did something right where you would have expected to have a maximum value. Let's say the function is not defined. And right where you would have expected to have a minimum value, the function is not defined. And so right over here, you could say, well, look, the function is clearly approaching as x approaches this value right over here. The function is clearly approaching this limit, but that limit can't be the maximum value because the function never gets to that. So you could say, well, let's get a little closer here. Maybe this number right over here is 5. So you could say maybe the maximum value is 4.9. But then you get your x even closer to this value and make your y be 4.99 or 4.999. You could keep adding another 9. So there is no maximum value. Similar here on the minimum. On the minimum, let me draw it a little bit so it looks more like a minimum. You can get closer and closer to it, but there's no minimum. Let's say that this value right over here is 1. So you could get to 1.1 or 1.01 or 1.0001. And so you can keep throwing some zeros between the two ones, but there is no absolute minimum value there. Now let's think about why it being a closed interval matters, why you have to include your endpoints as kind of candidates for your maximum and minimum values over the interval. Well, let's imagine that it was an open interval. Let's imagine an open interval. And sometimes, if we want to be particular, we could make, this is the closed interval right over here, brackets. And if we want to do an open interval right over here, that's A, that's B. And let's just pick a very simple function. Let's say a function like this. So right over here, if A were in our interval, it looks like we hit our minimum value at A. F of A would have been our minimum value. And F of B looks like it would have been our maximum value. But we're not including A and B in the interval. This is an open interval. So you can keep getting closer and closer and closer to B and keep getting higher and higher values without ever quite getting to B. Because once again, we're not including the point B. Similarly, you could get closer and closer and closer to A and get smaller and smaller values, but A is not included in your set and your consideration. So F of A cannot be your minimum value. So that's, on one level, it's kind of a very intuitive, almost obvious theorem. But on the other hand, it is nice to know why they had to say continuous and why they had to say a closed interval like this.